This is a lesson on the law of refraction in the unit on light and optics. In a prior lesson, I had mentioned how the path of light is altered when it encounters and enters into a second medium. We see that at that interface, the light comes in as a ray, intersects at that medium, and redirects as another ray. There's no bending, there's no curving in here for the light ray. There's two straight lines that change direction at that surface of the interface. There's a couple of vocab words that come in here. We're going to measure angles in here. You can see theta 1 and theta 2. The theta 1 is called the angle of incidence, and theta 2 is the angle of refraction, and that's the one that goes into the medium. Both of these angles are measured with respect to the normal here. So when you're doing problem solving, make sure you're identifying the angle with respect to the normal rather than any old angle just given in the problem. The law of refraction can be derived in several manners, and I've left that to you as an ambitious student to look in a textbook, either algebra-based or calculus-based. But this is what it comes down to. N1 sine theta 1 equals N2 sine theta 2. And the fundamental principle driving that relationship is that light will travel the path of least time. It turns out for it to travel along a straight line in here, the time to travel this line is going to be larger than the time to travel that line. And so that's where the derivation comes from and the driving concept there. So we get this relationship, N1 sine theta 1 equals N2 sine theta 2, and again, these angles are measured with respect to the normal. N1 and N2 can be any two values. You could have air and water, like it looks like here, oil and water, oil on glass, water on glass, glass on water, etc. It doesn't matter as long as you have this relationship set up well. And light can go from any one medium to another. It doesn't matter what those indices of refraction are. Often with this concept, they'll ask you conceptual or qualitative questions that require you to reason with this law without any numbers given. And often the terminology used is which way will the light bend from the normal? Will it bend towards the normal or will it bend away from the normal? And again, there is no bending of the light here. This is an initial ray, which is a straight line, and a second ray, which is also a straight line. We have a third ray here, which is again a straight line. There's no bending. But what they're talking about here is the relationship between theta 1 and theta 2. Does the light go towards the normal and theta 2 is smaller than theta 1? That would be bending towards the normal. Or is the second angle larger than the first angle and you have bending away? So this is a bending away and this is a bending toward. And the terminology there again refers to, does that angle get closer to the normal or farther away from the normal? That's the bending they're talking about. My tip here, in order to reason about it, is to think about values for sine. Sine of 0 is 0. Sine of a small angle is going to be a small value. Sine 90 is 1, so the sine of a large angle is going to be a large value. So if I have a situation where I have N1 sine theta 1, and I see that theta 2 decreases, which is what I have in this situation. Right? When I look at this situation here from theta 1 to theta 2, I see that theta 2 is less than theta 1. It's bent towards the normal. So if I see theta 2 decrease, in order to keep a constant value, that means that the index of refraction of the second material is going to be greater than N1. So N1 is less than N2. This may be a situation where we go from air to water. For instance, we know that the index of refraction of water is going to be greater than the index of refraction of air. And so we're going to get this light bending, what they call bending towards the normal. Okay. We can see in this the second interface between N2 and N3, we see that theta 2 is less than theta 3, that means that N2 must be greater than N3. I would say based on this final orientation here, I tried to draw a straight line through the initial path here. And if this final path here, which was copied over here, if these two were parallel to one another, I would say N3 equals N1, but that's not what's going on in this situation. Theta 3 is less than theta 1, so then I know N3 is greater than N1. So it may be that it went into oil rather than air again, maybe something like that. So that's how you reason with the law of refraction, is you remember that the sine of an angle, the values for sine of an angle, and then the index of refraction must increase or decrease in an opposite direction to what the angle increased or decreased. I have a couple of applications of the law of refraction that I wanted to share with you. The first is a really cool one about apparent depth. It says due to the path alteration of light emerging from the water. So if we have light coming from under the water, right, and then our eyes are receiving that light. If we follow light rays along there, we can see that it will leave with a larger angle than it hit the surface with. And when we follow those light rays back that our eye receives, remember our eye is not a very smart instrument perceptually. It thinks those rays came from this point Q, rather than doing the calculations and knowing that that light came from point P. So this is what we call the apparent depth. This depth of where point Q is, where the eye thinks the object is, rather than where point P is, where the object actually is. And you can see another example over here. There's two people looking at each other. The person outside the water thinks that the person underwater isn't as deep. The person underwater thinks that the person is farther away than what they really are on the outside of the water. So this is a very interesting effect. Another effect here is apparent bending of light with refraction of light. Light passing through material of non-uniform index of refraction. So I wanted to bring this up. To me, this is actual bending of light on some level. So what we have here is on the top picture here, the atmosphere is very dense near the surface, and it has a bunch of particles in it, dust particles, etc. And as you go higher up into the atmosphere, there's not as much air, there's not as much particles, there's not as much bending and refraction. So you do get this apparent bending of light from the sun through the atmosphere. And so we think the sun is actually higher above the horizon than what it is. And another effect here is like mirages. Light from the sky comes in, it gets bent along a very hot surface and comes up. And it may even look like there's water down here depending on the surface. So this is sort of how mirages start, or you get an extreme glare off the road, is the light bending down and coming up. One last effect that happens with dispersion is if there is white light hitting some sort of material, the index of refraction varies according to the wavelength of light. So we can see in here, if we have white light, which is all of the colors, that's the definition of white light, is it's not white, it contains all of the colors. We can see that there's a spread in here. For each color of light, for each wavelength, there's going to be a different index refraction. And you can see across here, here's water, 1.331, 1.332, and you can see how it's different for the different wavelengths. And that's why we get this dispersion effect, is because they will have, when they respond to N1 sine theta 1 equals N2 sine theta 2, well, the N2 is different for all of them, so they're all going to have a different angle. It'll get amplified again over where there's another point of refraction, and we get this spreading, this dispersion of light. If there's just a pure wavelength going through here, it will hit it twice and not get dispersed. But with white light, there's all the wavelengths in there, and it gets dispersed. I've left example problems for another lesson.